Our third paper is on the long-term effects of continuous keystroke authentication, which will be presented by Junho. Thank you, Junho.
Thank you. Hello, my name is Junho. I'm a principal engineer at SUNGSU Research. This paper studies the long-term effects of using continuous keystroke authentication on smartphones, and this work was done in collaboration with YOUNGHAN University. So keystroke-based authentication is about learning users' daily typing behaviors and training authentication classifiers. So classifiers are used continuously to verify users' keystroke information when users type on their phones. And if unknown typing behavior is detected, if someone else is typing on my phone, we'll detect it and we'll lock the phone. So the key usability challenge is that force directions will reject users' own keystrokes and lock them out from their own devices. Key security challenge is that imposters with similar typing behaviors might be able to bypass it. So in today's talk, I'm going to present some of the key deployment challenges and try to explain how we try to address them. So the first challenge is changing typing behaviors. So users' typing behaviors could change over time. Could be the holding positions could change, typing speed could change. The accelerometer and gyroscope values, which we use to extract features, can be affected, and these are very, very sensitive features. And we might encounter new typing postures and context. So users could be typing while leaning, walking, holding the phone with one hand, and the classifiers will just perform bad in unknown contexts. So if you have a test set that's so different to the train set, the classifiers can perform bad. So this graph shows real keystroke data collected over a 2-month period. It plots accelerometer M values, which are X, Y, Z values added together for 4 subjects. P2 values are quite consistent, and authentication classifier works really well for P2. But for P3, P5, P14, the raw values change significantly across different test sessions. So the authentication classifiers have problems. So we implemented existing HYOUNGHAN features, which are hand movement, orientation, grasp resistant features, and trend 1 class classifiers to show how the force direction rates change over time. So this graph shows force direction rates over a 2-month period. The P2 shows consistently low force direction rates because of the consistent raw data that we saw on the previous slide on the left corner, top corner. And for P3, P5, P14 shows inconsistent force direction rates, peaking at 100% for P5 and 60% for P3 and P14. So for these 3 subjects, the system is actually not that usable because the force direction rates are just too high at certain points. So our solution is frequent retraining. So we're retraining frequently to adapt to changing typing behaviors over time and learning about new contexts and postures. So this the graph here shows classification performance over a 2-month period. And the models are retrained using the proposed features, which I'll explain in the later slides. The red line represents no model retraining, so it shows high variations in the force directions. The dark green represents retraining model every 500 keystrokes. It's a quite frequent retraining scheme. It shows more consistent performance. The bands here represent the standard deviations. So we measured the average error rates across all users for each test session. We also measured force acceptance rates, which are text success rates, using samples selected from all other users as a text samples. So the red line represents no model retraining, and dark green represents retraining model every 500 keystrokes. Again, it's a very frequent retraining model. And this graph shows consistent force acceptance rate across all test sessions. So the authentication security is not really compromised even after retraining quite frequently. Second challenge is that smartphones have limited computing resources. So smartphone vendors expect model training to be really fast and should not slow down phones or drain battery. So we cannot train complex deep learning models on devices. And people are generally concerned about their keystroke data being shared with servers because it could contain private information. And this was revealed through our interview study. So we should avoid sending private keystroke data to servers for training complex model on servers. And these are very challenging constraints. But we really wanted to try this autoencoder approach to improve the performance of the system. So autoencoders are commonly used for anomaly detection purposes. So you compute the diff between the input data and the reconstruct output data, and you check the diff value against the threshold. So if the diff is larger than the threshold, it's considered as an outlier. And this approach was used for keystroke authentication before, and it showed really good performance. But the approach requires training user-specific autoencoders. So you have to train separate autoencoder for every user. But based on our deployment constraints, it's infeasible to train autoencoders on devices, and we can't really send private keystroke data to servers. It's not recommended to send private keystroke data to servers for training complex models. So our solution is transfer learning. We propose a novel transfer learning technique where we first train a common autoencoder on a server using keystroke data collected from about 20 people, which is generally good at reconstructing the output. And we use a common autoencoder on the device to reconstruct the output. And for a given user, we compute the diff between the input data and reconstruct output data. And we use the diff values as features to train lightweight classifiers on the devices. So the key idea is very simple. So we simply replaced the user-specific autoencoders, which are originally designed for anomaly detection, with a common autoencoder, which is generally good at reconstructing the output. We compute the diff on the device between user's input data and reconstruct output data, and we're measuring how well the common autoencoder reconstructs the keystroke data, and we use this reference measurement as features to train lightweight classifiers. So basically, we're measuring the competencies of the common autoencoder to reconstruct the output, and we believe this competency is going to be uniquely different for each person, and we use that information to identify individuals. So we trained light GBM classifiers using 4 different feature sets and compared performance in terms of equal error rates. We evaluated performance using the well-known public HMOG dataset, existing features, HMOGR features, and UniGraph features, which measure key restorations and touch XY coordinates that uses touch sensors. Showed equal error rates around 13 to 18%. Our autoencoder diff features showed equal error rates around 8% in the same settings, showing the best performance. So in conclusion, users' typing behaviors change over time and will encounter unknown typing context, unknown typing postures. Force correction rates for the original classifiers can actually get worse over time. So we need to frequently retrain the models to maintain low error rates. And our recommendation is that any behavior-based authentication systems should consider these long-term effects. They should study the long-term effects, and they should study how the behaviors might change over time and how it could affect the performance of the system. The proposed transfer learning technique involves replacing user-specific autoencoders with a common autoencoder, which is generally good at reconstructing the output, and using the autoencoder diff values as features to train light GBM classifiers on devices. So light GBM classifiers are sort of optimized for model training time and model size. So it only takes about 6-7 seconds to retrain a model. It outperforms existing HMOGR features, UniGraph features. And we satisfy all deployment constraints like not sending any private keystroke data to servers for training, maintaining low error rates, and not training any complex models on devices. So we recommend that any future work should also consider these kind of on-device deployment constraints for machine learning-based authentication systems. And that's it. Thank you. Thank you very much.
Thank you very much. We also finished in 7 minutes, so we have more time for questions. We can have 2 questions. Anyone? If you have a question, can you come here? We have a microphone.
Do you have any insight what causes those changes?
Oh, the causes of the behavior changes. So a lot of it are related to sort of the holding positions change, and the typing speed could change over time as well. And also, people could be typing like sort of unknown context. So unknown, like they could be walking while typing, could be leaning. They could be holding the phone with one hand with the other hand holding a cup or something. So there are lots of different unknown contexts that we need to consider affecting the performance of the system.
So do you see there's maybe some representative context? Instead of retrain the model, you actually store the model and switch the context?
Definitely. So there are more common contexts versus more rare contexts. So like leaning and walking are very common contexts that we consider, and we actually ask users to perform those contextual-based data entering process during the enrollment phase. So we actually have an enrollment setup phase where users have to type while sitting and standing, walking. So those are sort of the standard contexts that we really want to capture data. Now, when we retrain the model, we always use the initial data that we capture from the enrollment phase. So that's always contained as part of the retraining data set.
Okay,
Thank you.
Might have time for just one quick question, if there is any. Otherwise, we can leave it for the, okay. Can you come over here? Thank you.
So thanks for your presentation. So basically, I was asking myself from, I would say, from an industrial perspective, how do you